Hi, my name's Steve Campbell and I'm with the Robot Arm Project. My fellow teammates were Mike Brisbane and Matt Higgins, and in this project we were able to take a robot skeleton and implement the microcontroller to make it move. We also implemented a Python API to communicate with the robot via XB. This communication would allow the robot to be controlled remotely through the Python API. So in this video I'd like to take the time to go over the file structure of a repository and also go over an example of the Python code that we used for the demo at the end, as well as talk about some common issues that we had that can be improved upon. So as you can see here is our Bitbucket repo. It has 3 different folders if you disregard the IDEA folder, which is for IntelliJ IDE. The first folder, the Arduino robotic arm, contains all of the code for the microcontroller. The node folder contains a Node.js implementation of the robot API, which is incomplete. The Python folder contains a Python robot arm package, which is complete, which we use to control the robot in the demo. If we delve into the Arduino code, we can see that there's 2 files here. Robot.h contains a class called robot, which describes all the public functions for the robot, and it contains all of the code for moving the servos and manipulating the robot itself. So it's more or less the metal. The robotic arm.ino is the microcontroller read loop. It basically loops over the serial connection, parsing in robot commands, and then passing them off to the robot object that it instantiates to actually execute the moves in the environment. For right now, we'll skip over the node folder. So if we go into our Python folder, we see I have 2 files, 2 folders, examples and robot arm. I think examples is pretty self-explanatory, so let's jump into robot arm. The init file in this package is what makes it a package. So we can skip over that for now. The version is just declaring a version number. So the 3 interesting files in this package are commands, robot, and robot serial. Commands contains the protocol for each command, including move, rotate, arm up, and claw. The robot.py is an implementation of the robot itself. This is something that you would instantiate into an application and call things like robot.arm2, claw2, move2, go2, pickup, and those sorts of things. Robot serial actually is an extension. If we go into it, it's just an extending serial to be able to send robot commands. The open is a little bit different from the serial package in its normal form, and also the send command is an added function that we put on top. It basically listens for a retry. So if it failed to send the message, then it'll just keep sending the message over and over until it sees a success. You normally wouldn't have to do anything with the robot serial or the commands. You wouldn't have to import them into an application or anything like that. The only file that you would import is the robot class here. And you can see it's just a class robot. It has a couple of public functions that we'll talk about: arm2, claw2, connect, disconnect, drop off, go to, and pick up. And so those are all the public functions. As you can see, there's a bunch of private functions in here. They're well documented. If you are unfamiliar with Python, you can just import the package and type help parenthesis robot and parentheses, and you'll get all the documentation for this class, which would be quite helpful. So now we'll be moving on to talking about a Python example. As you can see, we're in the robot arm ns python examples test.py. This is the program that we use to create the demo at the end of the movie. In order to use the robot Python API that we created, it does have one dependency, and it's dependent upon NumPy. Now if we go over to NumPy's website, we can see that NumPy is the fundamental package for scientific computing with Python. And it has instructions on how to install NumPy, but basically you just have to go here. I think you can also install it with pip or easy install, so it depends how you would want to go about it, but you'd need that for a couple functions, and we'll talk about them in just a second. So right here is where we bring in the robot class from the package that we created, and we instantiate it on the next line. This dev TTY USB 0 is the USB port that you are going to plug the XB device into to communicate with your robot. We define 3 position arrays. So this is the pickup location, the drop-off location, and the origin. Now, the pickup location is an array which is organized as X, Y, and Z. And so the location of the item that we're about to pick up is at XY coordinate 30, 30, and the Z coordinate actually tells the robot how high up the arm will have to go to grab the centroid of the item. Next, we have the drop-off destination, and similarly, the drop-off is going to be at 87.9, and the height is going to be 22. And that's not the height of the rail that it's going to sit on, it's the height of the centroid of the object that you're carrying. That's important to keep in mind. And our origin that we're going to start off at is 0, 15. When the robot is instantiated, the default origin is 0, 0. And that's good to keep in mind. So right now we just read in some raw input for a pause, and quickly we used connect. Like I said, if you instantiate the robot class, it doesn't necessarily connect to the robot. You actually have to explicitly call connect. So then again we read in some like just a pause basically, and then we tell the robot to pick up at that position that we specified here. So it's going to travel 30, 30, move its arm up to 5, pick up the item, and then we tell it to drop off at this position. Then we go back to the origin. We lower the claw, or we close the claw rather, and we lower the arm to 0. As you can see, it's relatively simple to do the demo that we show you at the end of the video. I would like to take the next few minutes to talk about the protocol that we implemented for the robot commands that are being sent from the Python layer to the robot Arduino code, and also talk about some issues. So each command consists of 6 bytes rather. The first byte is always the command. The second byte can either be the padding or direction, and by padding we mean that it's just going to be a 0 byte, so all 8 bits of the byte are going to be 0. The second, it can either be the distance in centimeters, which is 2 bytes, or it can also be the angle of degrees. And the last 2 bytes are the checksum, which is the summation of the first 4 bytes. Next, I want to move on to some issues that we had. There were 2 major issues. One of them had to do with the tracking, and basically there was 2 parts of the tracking issue that we had. There was the wheel alignment we felt was not completely center, and that was actually making the tracking go to the left. And also, writing to the servos is done in such a way that you need to write to one servo first. So if we were moving forward, you'd have to write to the left and write to the right, or write to the right first and then to the left. But either way, one servo would start just a little bit ahead of time, and that would throw off the distance, especially if it was going a longer distance. So the vectors that you give it, don't be surprised if it doesn't land exactly where it should. We tried to change the code to write simultaneously to all of the pins on the Arduino, but weren't successful. You can try to go down that route as well. It was sort of towards the end of the semester, and we were not able to put everything together. The other issue is that, and I'm not sure if this is quite the issue or not, but I guess it's a guess, is that the movement of the wheels, thus the power going to the two wheels, are different, so that one servo is slower than the other. Now, I'm not sure if that's an issue, but we wrote it here as a possible issue. In the documentation that we gave you, there's a couple references that we had at the bottom. The NumPy dependency for robot, Python API we put here, our Bitbucket source code, and our Python serial docs. We also, if you scroll up, we have some other documentation. This is actually the structure of the breadboard and how we can hook it into the Arduino. If you look into the code for the Arduino side, you can see that we set up the pins for the arm in pin 3, claw in pin 6, left wheel in pin 9, and right wheel in pin 11. We had to make a common ground between the two. And it's also worth noting that the battery pack that comes with the robot is actually the power for the Arduino. It is not powering the servos. If you power the servos with that, you will most certainly burn them out unless you reconfigure the circuit in such a way to drop the voltage. And there's some more documentation here, but that's basically our project. I hope you like it, and I hope you guys can take it one step further than we have. Thank you.